Property modeling in Petrel is an essential module that allows geoscientists and reservoir engineers to create three-dimensional models of the physical properties of hydrocarbon reservoirs. By integrating well, seismic, and reservoir data, the software assigns key properties such as porosity, permeability, and fluid saturation throughout the geological model. Using advanced interpolation and simulation techniques, Petrel enables the visualization of the spatial distribution of these properties within the reservoir, helping teams plan drilling activities and optimize production. This integrated approach provides a powerful tool for managing and maximizing efficiency in resource exploitation. This workflow outlines the complete process for modeling and evaluating a hydrocarbon reservoir by integrating geological, petrophysical, and engineering data. It starts with the collection and interpretation of well and seismic data, followed by building structural and facies models to understand the distribution of rocks. Next, we assign key petrophysical properties like porosity and permeability, calculate hydrocarbon volumes, and assess uncertainty. Finally, the model is upscaled for simulation, and the well design is optimized, continually improving as new data becomes available during reservoir development. And always remember, you are making big decisions based on limited data. This diagram illustrates the property modeling workflow in Petrel, starting with data preparation, well log scaling, and the use of geospatial statistics to understand property distribution within the reservoir. It then moves on to facies modeling and petrophysical modeling, applying both stochastic and deterministic approaches. Finally, volume calculation and uncertainty analysis are performed to evaluate different reservoir scenarios and optimize decision-making. This diagram illustrates a comprehensive approach to geostatistical modeling using well-logged data and secondary spatial distributions. On the left side, the process begins with univariate and bivariate geostatistical modeling, which focuses on analyzing well-logged data to make geostatistical inferences based on frequencies and analogs. These stages help establish relationships within the well-logged data, providing key insights into the subsurface. On the right side, the approach expands to incorporate the use of secondary data through spatial distribution and advanced techniques, such as 3D co-criging. Here, 1D function trends, 3D local varying means, and probability maps are used to better understand the spatial properties of the reservoir. The goal is to generate a more accurate representation of the subsurface by integrating multiple data sources and advanced bivariate distribution methods, enhancing the accuracy and reliability of predictions in the final model. This process helps manage the complexity and uncertainty inherent in reservoir characterization, improving model quality and supporting better decision-making in exploration and production projects. This Petrel module offers two methods, stochastic and deterministic. The stochastic method generates multiple realizations to explore uncertainty and different scenarios, ideal for limited or uncertain data. The deterministic method provides a single, fast interpretation based on reliable data. Both approaches allow flexibility, helping you make informed decisions depending on your data and project needs. The image compares simulation and criging in reservoir modeling. Simulation generates multiple realizations to capture uncertainty and variability, useful when data is limited. In contrast, criging provides a single, smooth, and precise estimate, ideal for a deterministic and reliable interpretation. Both methods suit different needs, depending on whether you want to explore multiple possibilities or focus on one solution. In this lesson 2, the focus is on how to incorporate depot space into structural gridding. Depot space refers to the spatial framework in which sediment deposition occurs, and understanding its integration is crucial for creating accurate structural grids. This lesson will cover the methods and benefits of including depositional environments in grid models to improve the geological representation and the accuracy of reservoir simulations. In this figure, we compare the traditional geospace approach with the depot space model. Geospace shows the current structural space of the subsurface, displaying geological layers as they are today, including faults and deformations. In contrast, depot space reconstructs the space as it existed during sediment deposition, before any deformation occurred. This depositional model provides a clearer and more accurate view of how the layers originally formed, helping to better interpret the distribution of facies and reservoir properties. Euclidean distance and geodesic distance in a geological context where subsurface layers are deformed. In the top part, the Euclidean distance between 2 points A and B is shown across folded geological layers. This is the straight-line distance between the points, ignoring the shape of the layers, which does not reflect the true distance along the geological structures. In the bottom part, the geodesic distance is displayed, following the contour of the layers. Here, points A and B are connected along the layers, respecting their shape and folds. This distance is more representative of the geological reality, as it accounts for deformation and the actual path along sedimentary formations. In summary, geodesic distance provides a better representation of spatial relationships within the reservoir compared to Euclidean distance, especially in complex terrains with folds or faults. The image introduces two fascinating approaches to understanding a reservoir: geospace and depospace, each offering a unique perspective of the subsurface. Geospace shows the reservoir as it is today, complete with all the faults and folds that have developed over time. If you're planning to drill or need to understand how oil and gas move through these deformed structures, this is your go-to tool. It helps you design more efficient wells and understand fluid flow in the current reality of the reservoir. On the other hand, depospace takes you back in time, showing how the layers looked before tectonic forces altered them. It's perfect if you want to study how sediments were originally distributed or how reservoirs were connected before deformation. It gives you a clear view of the original reservoir, showing the sedimentary architecture as it was first formed without later tectonic influences. Which one should you need use? The key is to combine both. Geospace shows you the structure as it is now, while depospace reveals how it all began. Using them together gives you a complete understanding of the reservoir, from its origins to its present state, allowing you to make more informed and accurate decisions. It's the best way to see both the past and the present of your reservoir. The image shows how depospace reconstructs the original geological layers compared to their current state in geospace. In geospace on the left, the layers are deformed by tectonic forces with visible folds and faults. In contrast, depospace on the right represents the layers as they were at the time of sediment deposition, arranged in a much simpler and flatter structure. The image also highlights two key properties of depospace: subplanar isochrones. The depositional surfaces were relatively flat and uniform during sedimentation, as shown by the subplanar isochrones. Volume of interest. Any points not present in today's deformed space are outside the volume of interest in depospace, reflecting their absence from the original depositional structure. These elements help visualize how layers have changed from their original form to their current, more complex arrangement. The image illustrating property 3 shows how tectonic deformation has displaced points that were originally closer together at the time of deposition. In depospace, the geological layers and points are more aligned and uniform, whereas in geospace, the folds and faults have significantly separated these same points. This provides a critical view of how the reservoir structure has changed over time, highlighting how the original connectivity has been affected. This displacement directly impacts the interpretation of the reservoir, as the original connections between layers or reservoirs may have been altered, affecting the distribution and flow of resources in the subsurface, and ultimately influencing efficient exploitation. The image demonstrates property 4, which highlights how deformation alters the continuity of geological layers. In geospace left, we see the yellow layer with the red dotted line following a distorted path due to folding and deformation. This shows how the layer has been significantly bent and displaced over time by tectonic forces. In contrast, in depospace right, property 4 reveals the original continuity of the yellow layer. Here, the red dotted line runs straight, indicating that during deposition, the layer was undisturbed and uniformly distributed. Property 4 emphasizes how deformation disrupts the original continuity of geological layers and how depospace helps restore this original form, providing a clearer understanding of the initial geological structure before any tectonic alteration. The image compares two coordinate systems, XYZ, representing the present-day geological structure after tectonic deformation, and of the depositional coordinate system, which shows the layers as they were originally deposited. This transformation between the current and depositional states highlights how geological layers have shifted over time and the importance of using both perspectives to fully understand the subsurface evolution. The image demonstrates the process of using depot space for property modeling in a structural model based on a volumetric-based method VBM. The top left shows the initial structural model, created with faulted horizons, indicating the deformed present-day geology. The next step involves calculating and using depot space, where the layers are repositioned to reflect their original depositional state, as seen in the central image. Finally, the model is adjusted for property modeling, integrating the structural grid with depot space, allowing for a more accurate representation of the original properties of the geological layers in their depositional framework. This workflow highlights how transitioning from the current deformed structure to a depositional space improves the accuracy of property modeling. The image compares the classic SymBox view with the depot box view in the context of geological modeling. In the classic SymBox view left, we see the present-day, deformed state of the subsurface layers, reflecting how they have been shaped by tectonic forces over time. This view is useful for understanding the current structure of the geological layers, but shows a more complex and distorted arrangement due to geological processes. In contrast, the depot box view, right, represents the original undeformed state of the layers as they were deposited. This view simplifies the complexity of the geological structure, offering a clearer representation of the initial conditions before any tectonic deformation occurred. The classic SymBox view is effective for analyzing the current state of a reservoir, while the depot box view provides insights into the original depositional environment. The image provides an overview of the process settings and result for creating a structural grid using depot space in property modeling. On the right, we see the structural gridding setup window, where the user can define settings such as reverse faulting and enable the option to use depot space for property modeling. This setting ensures that the grid is built based on the depositional coordinates, providing a more accurate reflection of the geological layers as they were originally deposited. On the left in the model tree, the structural grid with depot space is listed, indicating that the grid is now based on the depositional space rather than the current deformed state. This grid is ready for further analysis and modeling of reservoir properties, allowing for a more precise interpretation of the original conditions before tectonic changes. This process is essential for obtaining a clear, accurate model of the reservoir's depositional environment, improving the reliability of property modeling. The images show the process of creating a structural grid using depot space for property modeling. In the first image, the structural gridding setup interface is displayed, where the option to use depot space for property modeling is selected. This ensures that the structural grid will be based on the original depositional coordinates rather than the current deformed state, providing more accuracy in modeling geological properties. In the second image, labeled sections A and B show the steps to access and calculate depot space. The depot space calculation tool is used to transform the current geospace model into its original depositional framework. The structural framework and horizons are also shown, indicating how the model is organized and set up for the grid creation process. Together, these images demonstrate the workflow for using depot space in structural grid creation, improving the accuracy of property models by accounting for the original geological conditions before deformation. Thank you for following along on this journey through structural modeling and property grids. By understanding how depot space brings us back to the origins of the Earth's layers, we've unlocked a clearer view of geological history and its impact on today's resources. I hope this insight inspires more accurate, efficient, and innovative approaches in your future projects. Until next time, may your explorations continue to shape a deeper understanding of the world beneath our feet. Stay curious and see you soon